Hello everyone, welcome to the second lecture of week 10. So in this week we have been discussing about various parameter efficient methods, and we started with parameter efficient fine tuning. So we'll continue the discussion this lecture as well. So we will talk about the parameter perspective of PEFT, and we will focus on LoRA as one of the main methods, and then we will discuss about certain variations of LoRA, specifically KronA and VeRA. We will talk about two such methods. So what are different perspectives to think about parameter efficient fine tuning? We talked about three perspectives, that you can do it in input, example like prefix tuning. You can do it at function, examples for adapters, or you can do it in the parameters, right? And that's what you'll focus on now. So we'll talk about one particular perspective, right, and how do you bring in efficiency in the terms of parameters. So let's go back to our original scenario. What do we have with us? So we have a pre-trained autoregressive language model, right? So that can give me a probability of y given x. So y can be a sequence, it can be GPT model or any other kind of architecture. So what is important that we are talking about pre-trained models already, and you have to do fine tuning for various applications. So this is what we are saying, that we want to adapt it to various downstream tasks like summarization and so on. Now for each task you will have some training data set, right? So with which you can do fine tuning. So like here you have n examples of input output. Given this task input, you have a corresponding output. Now what happens during normal fine tuning? So normal fine tuning, what you do, so I have some initial parameters phi naught, these are the pre-trained parameters, not like random parameters. So these are pre-trained parameters, and now I try to fine tune them. So it's like I find some delta phi, I add some delta phi to these parameters. And how do I do that? I have to do, I will have to maximize the language modeling probability or whatever objective, whatever loss I have, right, so that I can find the new parameters that work for that particular task, right. So I want to find the parameters that maximize the log probability of the next token in the case of GPT kind of models, right. This is the way we also fine tune them, increase the probability of the next token given the previous input. So that's what we do in the fine tuning, right. Now what is the issue with this, right? See, the updates that I am getting, this delta phi is of the same magnitude, the same size, right? The number of deltas that I am computing are same size as the initial parameter set, because for each parameter you are finding out how much it has to be shifted, right, with fine tuned model. So like take a large model like GPT-3 that has 175 billion parameters. So that means you have to find 175 billion changes, right, to all these, one for each parameter. Now that's where we get our key idea. The idea is that, okay, what we want, we are starting from phi naught, I want to find some delta phi. Now delta phi has the same dimension as phi naught, delta phi has the same dimension as phi naught. So can I have some trick by which I can approximate delta phi using some smaller number of parameters? So I want to retain phi naught as it is. I want to focus on approximating delta phi using some smaller size set of parameters. So something like delta phi as a function of theta, where theta is much smaller than phi naught, right. If I can do that, that means I just need to worry about a small size set of parameters like theta and not phi naught size, right? So that means I want to find phi naught plus delta phi as a parameter, as a function of theta. I want to find those theta parameters that maximize this loss, and that means I just need to worry about finding these theta, right, theta parameters, and this can make my task much more efficient, right. Rather than doing it for 175 billion parameters, I will do it for very small number of parameters, and we will see this number is much smaller than 175 billion. Okay, so how do we do that, right? I mean, I still have to follow the same process of doing forward propagation, backward propagation. So how will I approximate this change by a small set of parameters? So let's see. So we'll talk about the main model in this particular context. This is low rank parameterized update matrices, also known as LoRA. So what is the idea? Idea is that this update that you are talking about, phi naught plus delta phi. So these updates, people have shown that they have a low intrinsic rank, okay, when you adapt the model, pre-trained model, right. So we are talking about pre-trained model adapting to some new task. So the updates have an intrinsic low rank, right. So we make use of that fact, that is, okay, let's say my pre-trained weight matrix is of dimension d cross d, or let's say in general d cross k. Right. Let's take any matrix, and what is important is that R, the rank, is much smaller than the minimum of d and k. Okay, and A and B remain the trainable parameters. So you see, rather than having delta W that was of size d cross k, and let's say maybe k and d of the same order. So delta W was of the dimension of d cross k, which is roughly say d square. Now you are saying I have two matrices B and A. If I multiply, I get delta W as an approximation, and how many parameters are there? You have d cross R plus R cross k. So if d and k are same, this is 2 times R times d, and R is much smaller than d and k, right. So that's where you save, right. You have less number of trainable parameters than what you were having in your original formulation. Okay. So how do we train? How do we do inference in this scenario? So we are saying what we are doing. We are saying we will, when we are training, we will initialize two matrices. So we will say, okay, we will have W naught, we will have B and A. So any input will pass through both W naught and B A, right. So and W naught is frozen. I don't do any updates on W naught. I only talk about this delta W part. So W naught will not receive any gradient updates during training. So suppose this is what I want to compute, h is equal to W naught x, right. I have an input x, I want to multiply it with by matrix W naught. What will happen now? I am saying, so this will be W naught plus delta W x, the change that you want to approximate. So this will be the new set of parameters, and delta W I write as B times A. So this, in the forward propagation, I multiply x with both W naught and B A, right. So any x will multiply with W, also multiply with B A, and then I add these outputs and get my h, right. So this is what happens in the training time, in the forward propagation time. What will I do? And I mean, you will do back propagation. The gradients will only be received at B and A. So this is frozen, does not receive any gradient updates. Only these receive gradient updates. Now what will happen at the inference time? At the inference time, that means your B and A has been trained already, right, with your data. So you have found the B and A that maximizes the likelihood for your data, right, and your B and A are frozen. So at inference time, what will you do? So you know your new matrix should have been W naught plus delta W, that is W naught plus B A. Now you know W naught, you know B, you know A, and B A will give you the same dimension as W naught. So you don't need to separately pass through W naught and B A at the inference time. You can simply say compute the new matrix W is equal to W naught plus B A, and just forget whatever happened, right. I mean, you do inference the normal way you were doing. So you do inference with this matrix W. So it changes nothing at the inference time. This is different from adapters. Adapters are separate, right. The separate functions, you have to retain the adapters at the inference time. So they cause certain overhead at the inference time, but this will not cause any overhead at the inference time. So you will have the same matrix W that you started with. It will only help you in increasing the efficiency during fine tuning time, right. inference time, it is exactly the same as the normal normal weight matrix. Okay. Now the question is, which weight matrix in the transformer are this LoRA applies to, right? So you cannot apply it to the feed forward network because of this ReLU, right? There is a nonlinearity involved, so you cannot do that. So you only apply to matrices that are linear transformations. So you have query matrix, key matrix, value matrix, and the output matrix at every layer across each attention heads. So you only apply for those, right? And you can vary what is the rank that you want to keep. So like here you can, so like this example what is done, so you can either have a rank R for individual query key and value and not adapt anything else, or W naught, or you can take two of these like WQ WV and have a rank 4, right? WQ WV4, WQ WK with, or you can adapt all 4 matrices with rank of 2, so that your number of tenable parameters remain the same. Now how do I get this number? We will spend some time on that, right? How do I get this 18 million parameters here? It will spend some time. But what is shown here, even I mean across these, you see performance is very is better when you adapt WQ and WB. Right? This is typically working good. And what is the optimal rank for R? I mean, what is seen is that even with a small enough R, LoRa typically works better. So you don't need a very large rank. Even if you have a smaller rank, it works better for the kind of task that they have considered, right? I mean, it may not be generalizable across all the tasks, but at least certain tasks like NLI and classification, etc. LoRa with a small rank works good. Okay. So for example, like let's try to work this out. So how many parameters do you need in LoRa for fine tuning? So let's say we have GPT-3 model. So it has model dimension of 12,288, right? It has 96 layers of decoders and 96 attention heads. Right? So, and let's say take the first one, you take RV is equal to 2. What does that mean? You only adapt the value matrix, right? The value matrix, and its rank is 2. So how many parameters will you have? Okay, so let's break it down. So you have 96 layers. So you will do this for every layer, right? So you have 96 layers. So let's talk about one layer. In one layer, where will this value matrix feature? So you will have 96 attention heads, and each attention head will have a value matrix of dimension D cross D by 96, right? D cross D by 96. Okay, so that is the value matrix dimension. Now, do I apply LoRa there? No. So what exactly they do? So they say, okay, so you have 96 such matrices. So each matrix is D cross D by 96. So something like D cross D by 96. This is for the first attention head. Now you will have similar matrices for all the attention head. So you keep on just stacking them one after another. Right? So this is for another second attention head. So like that you will have 96 attention heads. And you see now, if you keep them in this particular arrangement, it will be D cross D matrix. You call it the value matrix for the layer D cross D dimension by putting all the parameters in this particular manner, right? Now you think of this as your weights, right? So think of this as your weights, and for this value matrix for a particular layer that is of D cross D dimension, the change you approximate using the LoRa. So that means you will have two matrices D cross R, another one R cross D, right. So this is what you will be approximation for the change in this particular matrix. So delta in this is approximated by this B and A. So how many parameters do you need per layer? You need 2 times d times r per layer, right? And then you have L layers. So how many parameters do you need? 2 times d times r times 96 decoders. So let's compute 2 times 12288 into r is 2. So this will be roughly 50k into 96, right? This will be roughly 4.8 m, right? That's what we get. I mean, if you do it exactly, you will get around 4.7 million parameters. So you see, I mean, otherwise, how many parameters would you have to tune? You would have to tune 175 billion parameters, right? So you are going from 175 billion parameters to 4.7 million parameters by making use of this LoRa configuration, right? And this looks very exciting. I mean, and then they have many configurations. So even if you use a 64 rank for all 4, so you can do it for query, key, value, and not all. Still, it's just 603.8 million parameters compared to 175 billion parameters, right? So this is huge reduction in the number of trainable parameters that you are talking about, right? And that's why this method has become so popular. Okay. Now, how does it work? I mean, in practice, when you apply this method to transformers, so you see these are applied to GPT-2, and this is a full fine tuning. You see the number of trainable parameters versus LoRa with right magnitude of 1000 less, and still you get better performance than fine tuning, right? I mean, that's very exciting, and that is across tasks. Yeah. So, and this is GPT-2 medium, GPT-2 large. In both cases, you have like 1000 times less parameters, and you are matching the performance of the full fine tuning, right? It is able to outperform even adapters and prefix layers and so on. And then they tried what happens if you scale it to GPT-3. So even in GPT-3, you see with say a particular configuration with 37.7 million parameter compared to 175 billion parameters, right? It was able to outperform on both WikiSQL and MNLI, right? So both the best models are with LoRa configuration, right? So even with GPT-3 scales quite well, and you can also, this was also nice plot that what if you increase the number of parameters. So this is for full fine tuning, so which has huge number of trainable parameters, right? But with LoRa, I mean, even with a small number of trainable parameters, you get a much larger accuracy than other methods, right? Adapters come close, but prefix layer and the prefix embedding, they are quite low compared to what you get by LoRa. And this has nice scalability, right? I mean, so, and you see with different rank, the performance is nearly same across LoRa. So this was a very, very interesting result that this paper showed. And I mean, this is a comparison of number of parameters, various PEFT methods. You can use prefix tuning with just the embedding, right, and prefix tuning with the layers. So what you need is the prefix and infix, right? You can use prefix and infix. So you can use adapter or you can use LoRa, and we worked out this particular parameters, right? And yeah, why adapter will be slightly higher, because you do 2 adapters, right, per layer. So it's slightly more trainable parameters, but in terms of performance, this is right nearly at the top, LoRa. Yeah. So we can, what you can do, you can try this problem that try to compute parameters for different kind of parameter efficient methods. So suppose you are using GPT-3 for query auto completion task, another task, right? So user types a prefix and your system tries to complete it. Now what you want to do, you want to personalize this to individual users of your system. So let's say there are 10,000 users. So you need individual copies, 1 per user, right? So what you can do, you can either use prefix tuning. So it's, you don't want to, I mean, store parameters for each user, right? Like 175 billion parameters for each user. That would be like completely infeasible. So what you can do, you can store very small number of parameters. How? So this is allowed by, for example, you can do prefix tuning, right, for all the layers, and let's say length of prefix is 4 and length of infix is 4, right. Or you can use LoRA for query and key matrices, 2 of the matrices with rank 2, or you can use adapters with the projection dimension as 2, right. So what will be the number of parameters? So let's find out per layer. So for prefix tuning, what are the number of parameters? So you have prefix 4, infix 4, so you need 8 extra trainable tokens times model dimension, right. That's all per layer into L, number of layers. So this is for prefix tuning. What will happen for LoRA? So LoRA you are doing for query and key matrices. Now we just saw with an example that how they will actually come up to D model times T model matrices by putting all the attention heads together. So that means how many parameters? D model cross R cross 2 for B and A. For one, say this is for query, and similarly for cross 2, this is becomes for query and value matrix into number of layers L. So these are same, prefix tuning and LoRA will use the same parameters in this scenario, right. 8 times T model 8 times T model into L, yes, and LoRA is using 2 into 2 into 2, 8 times T model into L. What about adapters? So adapters roughly, so you have D model that will go to dimension 2, and then you will project 2 back to. So D model into 2 plus 2 into D model, but you will have the bias terms also, right, plus D model plus 2, and then you have 2 adapters into number of layers. So if you say this will roughly 10 times D model into L. So you see adapters will have slightly more number of parameters in this setup than the others, and of course this is for per user, this is per user. Oh sorry, I wrote per layer, so we are anyway multiplying with L. So now this is per user, right. So you will have to multiply these with 10,000 users, right, so individually into 10k users. So that many parameters will be required, right, totally to for this task. Okay. Right. Now let's talk about some variations of LoRA. Now one thing that people talked about this is that it has a bottleneck because you are doing low rank decomposition, so your representation power may be limited. So why don't we use a method that is not inherently low rank, but still can give me a reduced set of parameters, right. You can still reduce the number of parameters, but you may not be still low rank, right. So this was one method, KronA, parameter efficient tuning with Kronecker adapter. So this was one particular method. Then there is VeRA, that is vector based random matrix adaptation. So this will reduce even the number of trainable parameters even more than LoRA while maintaining the same number of performance. So let's see how these methods actually work. So this is the KronA paper, Kronecker adapter. So this picture compares, this is LoRA. So you have X, you multiply with A and B, right. This was your D cross R, R cross T. This is parallel adapter, right. So we talked about this. So you have adapter in parallel to the module. Now what KronA does? So let's focus on B. We'll talk about D slightly later. So what you will do? So you will have another 2 matrices, AK and BK, right. Very similar, going very similar as LoRA, but rather than doing multiplication, you do Kronecker product between the matrices. Okay, and that is the only difference, right, compared to LoRA. You have 2 matrices, but the dimensions are different. This is D cross R, R cross T. This is A1 cross A2, B1 cross B2. How are they connected to D cross D? We will see. And what is this Kronecker product? Right? Yeah. So let's say we have 2 matrices A and B, and we are taking a Kronecker product. What does that mean? So let's say A is of dimension A1 cross A2, and B is of dimension B1 cross B2. So what will you do? So you will take the first element of A, right, that is A11, and then you put the entire block of B, B1 cross B2. So, you have an entire B1 cross B2 block here. And this is multiplied by a single scalar. So, this B1 cross B2, that is B matrix, each element is multiplied by A11. So, you have your B1 cross B2 block covered. Then you have the next B1 cross B2 block, where each element of B will be multiplied by A12, like that. So, last one, so A1n. So, how many, what is the, how many columns are there? So, B2 cross the number of columns of A, that is A2. So, this is B2 cross A2, the number of columns. Similarly, how many rows are there? So, you have B1 already covered here, and then you will do it for each A11 to AM1. So, that is number of rows of A. So, you will have A1 cross B1 is the number of rows here. So, what you have to ensure, A1 cross B1 should be equal to, if W is W1 cross W2 should be equal to W1, and A2 cross B2 should be equal to W2, right. So, that is what you have to ensure. So, here A1 cross B1 should be DH, and A2 cross B2 should also be DH. So, that is one constraint that you have to put, and that is how this Kronecker product is defined. Interesting. So, and you see this does not have to be low rank. Now, this is one example on how you do Kronecker products. So, let us say you have two matrices 1, 2, 3, 4 X and 5, 6, 7, 8, 9, 10, and you want to compute X Kronecker product with Y. So, what you will do, you will take one element of X 1 and multiply with the whole Y matrix. Next 2 whole Y matrix, 3 whole Y matrix, 4 with whole Y matrix. So, what will you get? 5, 6, 7, 8, 9, 10, 2 multiplied with that, 10, 12, 14, 16, 18, 20, right, 3 multiplied by that, and 4 multiplied by that, right, and you get the your dimensions 2 cross 2, 2 cross 3, right? 4 and 2 cross 3, 6. So, you also can do Y cross X, dimension will be same, the real will be different, right. So, they are, so you have a different, these two are not the same, right. So, this is an example of Kronecker product, right. So, let us compare LoRA with KronA. So, you will have, how many trainable parameters are there? You see, that is the crux, how many trainable parameters are there. So, in LoRA we had 2 times DH cross R for a rank R, right. In KronA I have 2 matrices. Once I have 2 matrices A and B of size A1 cross A1, A2, B1 cross B2, I simply do a Kronecker product, and I get my delta W, right, that I want to preserve. So, how many parameters are there? A1 cross I2 in the A matrix, B1 cross B2 in the B matrix. So, that means this is the number of model parameters. So, only constraint is A1 B1 should be equal to DH, A2 B2 should be equal to DH. So, if you think about it, let us say they are of the same order. So, A1 and B1 are roughly say square root of DH, right. So, then how many parameters will be there, and same with A2 B2. So, then you will have DH plus DH, 2 DH parameters, right. So, you are saving on the parameters, you have only 2 times DH parameters compared to DH cross DH in your update. A good thing about KronA is that unlike the low rank projection used in low rank adapter, it maintains the rank of the input matrix, right. Good. Now, but you may have a question, okay, but at least in the case of LoRa, when we have had X, I was multiplying it with W and I was multiplying with A and B in some order, right. So, this was fast because A and B both were small matrices, right. So, I multiply X with A, then I multiply with B. So, this was fast. But here what will I have to do? Once I have AK and BK, will I have to multiply X with this entire delta W matrix? So, this will be much larger, right. So, this will be take same time as multiplying with W. So, do we have a saving there also when we multiply X with this whole matrix, right. So, what I am saying is that when you multiply X with this is easy, simple multiplication, right, to a small matrix, another multiplication with a small matrix, and you get the output here compared to multiplying with this whole square matrix, right. But how would I do with KronA? I mean, will I have to first compute this square matrix from this and then do multiplication? That will be more inefficient. So, turns out There is a nice property with Kronecker product that you can use to even reduce the number of computations there. Right. So what is the property? So you can reduce the number of flops. You can avoid the reconstruction of this delta W. Let's call it delta W to be consistent with LoRA, and use this nice important property of a Kronecker model. What is that? So if you have A and B Kronecker product multiplied with the vector x, that is same as, now how do we read it? So you have, so first let's read inside the bracket, A transpose is EG, then you are applying a particular operation over x. See, x is a simple vector. So what you are doing, you are reshaping it, reshaping this vector x of some dimension m n into, or a vector x into B2 cross A2 matrix. So you are reshaping x into a matrix of size B2 cross A2. Of course, x has to have B2 cross A2 elements to start with, and then you multiply with B, that is okay. And then finally, the output that you have of this whole thing, you are doing another reshaping. That is, what it will do, it will convert this matrix inside into a vector. So you keep on stacking the columns, right? So if this matrix has multiple columns, you stack the columns. So column 1, column 2, column 3, and it becomes a matrix to a vector. So this is gamma, and eta does the other thing. So you convert a vector into matrix. Right? But yeah, why does it work? I mean, let's see why does this even work. So to understand, let's see a particular scenario. So you have this is your delta W matrix. You are writing it as A Kronecker with B. A is A1 cross A2 and B is B1 cross B2, right? So how do you write this? So you have A11 multiplied with the entire B matrix. Yes. So that means it has B2 columns already, right? And like that you do up to A1n. So it has A2 such blocks of size B2. So you have A2 blocks of size B2. Overall size A2 cross B2. Similarly, in terms of rows, you have each B is of size B1, and you have B1 blocks. You have A1 such blocks, right, of size B1. So you have A1 cross B1 size here, and of course A1 cross B1 is TH, A2 cross B2 is TH. So you have a square matrix. Okay, and you want to multiply this Kronecker product with a vector x of dimension TH again. So yeah, now what you can do, I mean, to understand that why this is equivalent to this particular thing. So you think about what is happening. So let's say x is of dimension dh, which is nothing but B2 cross A2. So you can think of x as some blocks of size B2. So how many blocks? A2 blocks of size B2, right? B2, B2, B2. Now what will happen? So you see this block B2 will get multiplied to x, right? And what will the final output? I mean, dh cross dh multiplied by dh cross 1, you will get it dh cross 1, right? You will get a dh cross 1 output. Let's first see that the outputs are of the same dimension of this. So you have A transpose should be A2 cross A1, right? A2 cross A1, good. B is B1 cross B2. And what about this thing? So you take x and reshape it into matrix of size B2 cross A2, right? Possible, B2 cross A2 is the dimension of x. So x is reshaped into B2 cross A2 matrix, right? And you see, if you multiply these, what do you get? B1 cross B2, B2 cross A2, A2 cross A1. So you will get a matrix of size B1 cross A1. Yeah, and then you apply gamma. What it will do? It will just keep on stacking its columns. So you have first column has B1 elements, next column has B1 elements. How many such columns? A1 columns. So you will have B1, B1, B1. So like that, A1 columns. So B1 cross A1, and that is also DH. So you will get a DH dimension output. Right. So this at least in dimensions makes sense. And why in values? So let's take at least one computation. So what is happening? So let's take this block of size B2, right? So this, you see A11 is constant here, A11 is constant. So what you are doing, you are multiplying B11 up to B1, say B2, B1 is of B2, right? You're multiplying these with x1 to xb2, and whatever is the result, you are multiplying that with a11 in the initial things. So, is that happening here also? So, you see when you reshape x, so this is nothing but x1 to xb2, right? The first b2 elements come here, and this one is b11 to b1 b2. So, you first multiply these b11 x1. So, this is same multiplication, this multiplied by this, same operation happening, and then whatever is the result, that will be stored in this b1 cross a2 matrix. So, this will be the first first element of that will multiply with a11, right. So, this thing will be multiplied by a11, right, and like that. I mean, you can verify this is the same thing, but I have at least shown you for given you a hint that this is actually the same operation. Now, that is a trick. That means I will not have to do this computing this matrix and then do multiply by x. No, I can simply do the simple multiplications. And how many are there? So, now you can see they are all small matrices now. You are working with a small matrices. So, it is very similar to LoRA in that sense, these computations. In the KronA paper, they tried other variations also. For example, one thing they said you can, so the previous block we talked about KronA, they apply to the weight matrices only. What do I mean by that? So, they are all not feed forward network. So, they are all like query, key, value and W0 matrices, and then they are merged to the original PLM like you do with LoRA. So, it does not increase the inference time. It is exactly same as LoRA, but you do not have the low rank problem. So, you have xw plus this is a scalar multiplication. So, even with LoRA, I mean people tried with scalar multiplication, that seemed to work better. So, you have a scalar multiplication to x times ak Kronecker bk, and so this becomes your tuned matrix. So, you merged it at the inference time, a single matrix to work with. Now, this does not adapt the feed forward network. So, they also tried variations by adapting feed forward network, but then you cannot save inference time, you will have to save them separately, right. So, you will have, it will work like a parallel adapter, right. So, you will not be able to merge these. So, they tried FFN block, so they call it KronA B matrix with the for FFN blocks, right. They call that blocks, the FFN blocks, which is a so same formulation except that it is applied with a feed forward network. And then they also tried the residual connection, so you can feed x back. So, this was the KronA B residual matrix. So, these are the three variations that they tried: KronA, KronA B and KronA B residual. And in terms of performance, you see, I mean all three work quite close and better than the previous methods that were available, right. And if you see the inference latency, if full fine tuning is 100, LoRa is 100, KronA has 100, right. Adapter has more, right. Adapter parallel adapters have more, and so also for KronA B and KronA B res, they have more inference latency, right. So, KronA is like a like to like replacement for LoRa, where you will not have any extra inference latency and you do not have to worry about a low rank problem of LoRa. Okay. Now, let us talk about VeRA. I mean VeRA, we will come back to the same sort of formulation as LoRa with very small change. So, what LoRa says, okay, in LoRa you have this A and B matrices, right. So, they are low rank matrices with rank R. Every layer you have separate matrices, right. So, what VeRA does is, okay, why do not I just use some A and B, they are some random parameters, and you freeze them. So, they are not trainable, they are frozen, and you share them across layers. But what you learn is how do I scale these across layers separately. So, you will have separate scaling across layers, right. So, you adapt them with trainable vectors D and B, and that will reduce the number of parameters. So, rather than having every A and B in each layer, you say A and B are fixed, right. You initialize them randomly and you fix them, freeze them, but you say I can change the scales of A and B. by multiplying with some diagonal matrix D and B. Okay. And so the only trainable parameters are just 2 vectors per layer, D and B, 2 vectors per layer. Rather than having 2 matrices per layer, you will simply have 2 vectors per layer, and that shows a huge, decrease in the number of trainable parameters, right? And also you can try to have a high rank, right, because of this. So let's compare the formulations. So in LoRA, what you do, you have W naught x plus delta W x, and delta W is written by B times A, right? So R is much smaller than minimum. And so how many parameters? So if W is D cross D, so you have D models times 2 times R into number of layers. That many parameters. Okay. In VeRA, delta W is written as, so you have a diagonal matrix. So underlined is the trainable parameter multiplied to B, and this is what will control. So whatever is the B, you will have this diagonal matrix. So what is the dimension of delta B? So B is M cross R. So delta B will be M cross M. So only diagonal values will be non-zero, other values will be 0. Right. So only M trainable values. Delta D similarly is R cross N. So this will be R cross R. Right. And only these R diagonal values will be trainable. And then you multiply with X. Right. So how many parameters? So you have M plus R, and M is roughly D model. So D model plus R parameters per layer into LTune. So you see, you save a lot here already. Right. So rather than having a multiplication by R comes as a plus sign here, and because of this you can afford to have R to be quite high. So R can be high here. Okay. So what is happening? So your B and A are frozen, and they are randomly initialized frozen. You can save the random seed. Now you simply multiply the values of this by delta B. So this will simply scale the rows separately. Every layer you can have separate scaling, and delta B will be say D cross D matrix, where these values can be say 2, 0.5, 3, -2. So they will have separate scaling per row and column. So only these D values. And if you see the number of trainable parameters, you go from, say, if you even use a high rank 256, while LoRA used 9.4 million parameters, it is just 24.5 K parameters, right? So you have a huge reduction. If you go for high rank, you have a huge reduction in the number of parameters required by VeRA in comparison to LoRA. So that's why you don't have to bottleneck yourself with just a small rank for LoRA. You can use VeRA with a high rank, but in a different formulation where you don't have separate A and B's across layers, but you will have trainable vectors that are multiplied to. So they are just scaling these A and B separately across layers, right? Different rows, different columns can be scaled separately. So yeah, and in terms of performance, of course, it's not very far from LoRA. It gives reasonable performance, right, with a huge reduction in the number of trainable parameters. Okay, and yeah, this book gives a little bit idea about these methods that we discussed, and we will continue and see what further from LoRA and kind of methods, right, what next we can do for improving efficiency in training. Thank you.